All right, so good afternoon. Most of you I have. I'm Dr. Eric. We're going to go over geometry. The focus for today is similarity and congruence. If you are facing with your back to me, that is not a good use of your time. So you need to separate yourselves and turn so you're facing this way. We will be out of here by 3:20, even though we're starting a little bit later than I expected. For similarity and congruence, we're going to be looking at Unit 1 transformations and Unit 2 congruence. This presentation, I will uplink to the YouTube channel. If you don't know, if you go to YouTube and you type in South Gwinnett Geometry, you're gonna come to my YouTube page. And this video, which we're streaming live right now to YouTube, as well as other videos will be on to help you for the EOC. So what I did is, because I prefer to write on paper instead of like kind of draw, I printed this presentation out, but I'll also put this on YouTube. What you have in front of you is just the questions. So if you have your red books, I'm talking about the first part of the red books. If you don't have your red books, that yellow sheet of paper that you picked up by the wall, that's where the crazy quick review sheet is, and you can also look stuff up right there. Just to go over a couple more days, so today we're talking about similarities and congruence. On Monday, we'll start more on time. We'll do 2:20 to 3:20. That's all things circles. So we're gonna be talking about central angle, inscribed angle, interior, exterior, equation of a circle. Anything with circles we'll talk about on Monday. On Tuesday, I'm calling it odds and ends. That's going to be volume, density, probability, trigonometry. If there is only one other day that you can come to, that one other day will be next week, Thursday. Next week, Thursday, I'm doing the crazy review where I cover every single topic that, like, not in depth, but I just go quick through every single topic, and that will go till 4 o'clock, and there will be food. So that is next week on Thursday that we'll start to go over that. And so I'll start having the food out at 2:20. I'll start teaching at 2:30. So right now we're doing geometry. A couple things I want to remind you about. When you come to decimals, it's really important for rounding. The EOC, what they're going to try to trick you on is making sure that when you round decimals, so I'm just going to spend 30 seconds to remind you, whenever they say thousandths, when you think of a decimal, this is the ones place. You should have learned this in 4th grade, but then you have the tenths, hundredths, thousandths. So what you're doing is you're looking, okay, they want the thousandths place, so I'm going to look at the place next to it. If that number is between 0 and 4, this number in the thousandths stays the same. If this number is bigger than 5, then the number in the thousandths goes up. So for example, if they wanted me to round this number to the nearest hundredths, next to the hundredths, this is the hundredths. I have 51.048. This is my hundredths. Because this number is bigger than 5, when I rotate it, my answer will be 51.05 when I round it. So make sure you know how to do rounding, because it is like them to trick you up and give you ones that are rounded incorrectly, just to see if you know how to round. Next, simplifying fractions. They will also have things where you have to simplify fractions. If you stink at simplifying fractions, just turn everything into a decimal. On your calculator, you would just type in 24 divided by 40, get the decimal, and then from there, you'll be able to see which multiple choice answers work. So I've got 0.6, so then I would test which of these would give me 0.6, and that'll be your answer. So if you stink at reducing fractions, find the decimals and compare the decimals. That's the same if you get square roots. So for example, if you don't know how to reduce the square root of 32, the way that you do reduce it is you think, okay, what perfect square can go into 32? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. 16 goes into 32 2 times. The square root of 16 is 4, so my answer is 4 square roots of 2. But let's say you didn't know that, and if I went too fast, that's okay. We're streaming live on YouTube. You can look at it later. But if you didn't know that, you can just take the calculator, type in the square root of 32, get the decimal. Sugar shoots, I'm in the wrong mode. Make sure you're in classic. On the EOC, you'll have an online calculator. So you can just, the online calculator won't give you math print. But I get a decimal, 5.6. You would type in all the answer choices. Whichever one gives you 5.6, you know is the simplified radical. So we're going to start off by talking about transformations. I'm going to go a little bit quick because most people do well on transformations, but let's just look at some highlights. You will need to know the concept of isometry and rigid motion. So when we have isometry and rigid motion are synonyms. They mean the same thing. What that means is that no matter what happens, congruence is preserved. And congruence, not only is it preserved, but the order of the letters is preserved. Anytime you have congruence, you're going to have equal sides and you'll have equal angles. The other type that you have is dilations. Dilations deal with symmetry. So for dilations, I'm sorry, not symmetry, they deal with similar figures. Dilations and similar figures only have equal angles. So the difference between congruent and the difference between similar is the sides. For congruence, the sides are equal and the angles are equal. For similarity, the sides are proportional and the angles are the same. So let me give you an example. If you are one of my kids, you should be in the red book looking at the crazy quick review, which is this paper. And I have it right here in bold print, sides proportional, angles same. So a lot of what I'm showing you is also from this crazy quick review. So the three things that deal with rigid motions and isometries are reflections, flip. We talked about how there's an FL in reflection and an FL in flip. Translation, slide. Here's an SL in translation, SL in slide. And then rotations, turn. And we've talked about almost like a steering wheel, like you have your driver's license. And for rotational symmetry, that dot's in the middle. And we'll talk about more of that in a second. To deal with reflections a little bit more, there's always these formulas that you can look at, but the two main things to remember is, and now it's still on that page, but you can also flip a little bit in the beginning, is when we reflect over the x-axis, the y-axis, or a horizontal or vertical line, you always need to do perpendiculars. So if we're reflecting this way, we're gonna form a right angle and count boxes. That's how it is. Here there's 2 boxes, so it's 2 boxes here. Here there's 4 boxes, so there's 4 boxes here. If you reflect over a line that's y equals x, like this, you still have to come up with the right angles. The way that you come up with the right angles is you need to have it intersect the line of reflection. So that means since y equals x, this is actually the line y equals negative x because the line's going down. We are counting diagonal boxes. So if I counted straight across, this is not forming a right angle right here. So I wouldn't count straight across. I always have to get a right angle. Basically, this line of reflection is a perpendicular bisector. So I count diagonally, 1.5, 1.5. Here, it's 2.5. Here, it's 2.5. Here, it's a half box diagonal. Here's a half diagonal box. That's the reflections. When it comes to rotations, rotations are turns. We talked about putting our hands in front of us, and this is our X and this is our Y, and every time we flip 90 degrees, we flip our hands. So if it's like a 90-degree flip, if this is 2 and this is 3, this is now 3, this is now 2. If it's a 180-degree flip, 90 plus 90 is 180, so we flip back. Then we flip back. It's just back and forth, back and forth. That's the whole premise. Okay? Remember that it's either clockwise or counterclockwise. And clockwise goes in the way of the clock. That's clockwise, counterclockwise goes the other direction. Translations are almost the easiest. Translations shift. We shift by adding and subtracting. So how much up, down, left, right, and that's it. Add, subtract, and we move on. So now you're going to look at the paper you picked up today. Let's look at U1, Q1. It should be the first question of what you picked up. There's more copies up front if you don't have it. This says it wants a translation of -3. You can stand up and get it if you don't have it. It's totally fine. -3, +1. Actually, can you switch calculators with me? Because I grabbed this one for you and I need the pink one. Because I figured you would. Okay. So all I'm going to do is each of these points, since this says x minus 3, I'm going to subtract 3. Because this says add 1, I'm going to add 1 to the y. So this point here is, let's say, -1, -2. So I'm going to subtract 3 to the left, 1, 2, 3, and then it says add 1 and go up 1. So that would be my new point. Next one, I'm still going over 3, 1, 2, 3, add 1, here's my second point. 1, 2, 3, add 1, here's my third, and then I have my translation. Again, if I'm going fast, we're recording it so you can watch it later. Reflect over the x-axis. The x-axis is a horizontal line, so we always have to form the right angle. So we're going to count. Here to here is one box. So here to here is one box. This is my new point. Here to here is 2. Here's 2. Here's my next point. Oh, I missed this one. Here's 2. Here's 2. So now I've got my shape, and I have my reflection. So they will try to trick you. Like it says x-axis, sometimes we just instantly think y-axis. So kind of pay attention to where it is. So that tells you how we're doing it. Here's another example of the y equals x. We're counting diagonal. This way is one box, so this way has to be one box. Except I lost my line. Okay, and then here's our next one. And then you can keep going here. Here's 1, 2, 3 across, 1, 2, 3 across. And now I have my box. My rectangle is proper math terms. If you need pencils, I have pencils up front. So you can definitely get a pencil. This one's reflecting over y equals negative x. It's the same thing. You can remember the rule. I never remember the rule, and I'm a geometry teacher. I just count boxes. One diagonal that way, one diagonal this way. This point stays the same. You probably use the term invariant. Remember, we've been talking about the term invariant. Okay, then we're going to keep going. This one is 1, 2 down, 1, 2 down, and then you have your box. Okay, invariant points are just points that don't flip-flop. That's it. Okay, next. We're going to go down to U1, Q2. Now it wants us to see, okay, what happened? How did we get from one place to the next? Now it's really important that we pay attention to the letters, because if we don't pay attention to the vertices, we're not going to know the correct order, because everything has to match up. So because it says A, B, C, D, P, Q, R, S, A is going to go to P, B has to go to Q, C goes to R, D goes to S. That matters. That helps us understand if it's a rotation or not a rotation. So for A to get to P, I sometimes just mark at least one set, so I can forget everything else. I just think, how could A get to P? So I would do this maybe for it being a rotation and then a translation. So if it rotates 90 degrees this way, this B ends up staying in the same place. The C comes right here. The A is up 4. And the D is like this. So first I see a rotation that's clockwise of 90 degrees. You did not have to do it this way. You could have done it another way. This is just one way that I noticed. After that, I say, okay, how can I get this A point that's now all the way up top down to this purple one? Well, it's just going to be a translation of 5. And then, well, it doesn't go over at all. So it's x0, y negative 5. You could, let's see, could you reflect it too? I don't think you could. Yep, I don't think you could. Let's look at this next one. Same idea. This is helpful. I would pick C as the point that I look at because it's so different than the other points. So I'm thinking, okay, how does C get to R? Well, in order for C to get to R, it's got to have some kind of flip. Okay, because see how it's kind of pointing up here and now it's pointing down. So I would say the reflection would be at y equals 1. That's going to put it down like this, and then it'll translate over. If you rotated it, then it would end up having this point would be over here. So it's going to be the reflection. Good question. So now we're going to talk about composition transformations. I don't know if they're going to show you this kind of, I'm just blanking on the word, symbolism, I guess. If they do, if you do see the 0, remember that what comes ever after that 0 is what is first. So this is saying a reflection of 90 degrees after a translation of 3 negative 4. If you don't do this, it will be wrong. They'll probably give you both. So you have to remember that if you see this of, Whatever comes second, you really do first, and this is first. So this 0, this little circle here means after. So rotate it 90 degrees after you do this first thing. So like here, this is a translation of x3 negative 4. All right, so we're going to jump down to question number 9. Jump down to question number 9. U1Q9. Okay, this one's a sequence of transformations. Again, it gives us the order A, B, C, R, S, T. So we know that A has to go to R, B goes to S, C goes to T. So I'm just going to mark the right angle because sometimes it's easier for me to pay attention to the right angles. So I know that the right angles, the orientation has flipped. So I know there's got to be some kind of reflection. So because C and D, because it's flipped, I know it's a reflection. If it was a rotation, then it would be pointing down. And because the orientation hasn't changed, I know it's a simple flip. So it's not going to be C or D. I notice the difference between A and B are they're exactly the same except for the last sentence. So I'm going to not confuse myself and just cross out the first part. So I know it's going to be a reflection on y equals negative, or x equals -1. So this is where it's going to start. So now the question is, how far do I bring it down? Remember, I care about the right angle. That's the one I'm looking at. So to get from this right angle to this right angle, do I subtract 1 or do I subtract 5? 5, yep, excellent. So it's choice B. Now we're going to talk rotational symmetry. Rotational symmetry is so easy, and there's probably going to be 1 or 2 questions on it. So if you have to only memorize a few things, make sure you memorize the rotational symmetry. It's worth your time. For rotational symmetry, all you're doing is you're taking 360 degrees, and we take 360 degrees because there's 360 degrees in a circle. That's why. Then you divide it by the number of sides in the shape. So in this shape, it only works, you can only do that if it's a regular polygon. Otherwise, you got to use your brain and figure it out. But in this shape, there's 3 sides. So all I'm doing is I take 360 divided by 3, and I know that every 120 degrees, it's going to map on top of itself again. This is the steering wheel problem. So it's if you turn it right in the perfect center. That's how you can do it. So I know at 120 degrees, it's going to look like that. And if I turn it another 120 degrees, 120 plus 120 gives me 240. And that's how I get it. So let's look at a couple problems. Let's look at this pentagon problem. We're going back up to U1Q3. U1Q3, front page again. So it's not going to be a reflection because the only reflection it could possibly be, if it was a reflection, would be a reflection on the y-axis. Now that's not completely true because technically I could also reflect it on this diagonal line and this diagonal line, but for our purposes, it's not a reflection. It's going to be a rotation. So we're going to take our 360 degrees. How many sides are there in the shape? 5. So that gives us 72 degrees. 360 divided by 5 is 72. So, but 72 is not one of our answer choices, but that's fine. All that means is we turned it just one time 72 degrees. If we turn it another 72, 72 plus 72 is 144, which is our correct answer. Okay, so sometimes you just have to keep adding 72. If 144 wasn't there, add 72 again and get 216. If that's not there, add 72 again and get the next number. Okay, so far so good? Here's another one. Now, these two are tricky because they're not regular pentagons or sugar shoots. They're not regular polygons. So we can't just divide by the number of sides. The only reason we could divide by the number of sides is because the previous image, all the sides were equal. So what we're going to do is we're going to have to figure out where else can we do something with it. Well, if we rotate this shape, even if we rotate it 180 degrees, do you see how the long side is pointing to my left? I think all of our lefts, right? So if we turn this 180 degrees, well, if we turn it 90 degrees, it's not pointing to our left anymore. The long side's pointing up. If we turn it 90 more degrees, the long side's pointing to the right, so that won't work. If we turn it 90 more degrees, the long side's pointing down, so that doesn't work. So we know it's not going to be a rotational symmetry. So now we'll see, okay, well, where can we draw a line that if we fold it, it will match up perfect? So if we fold it this way, we'll end up having the long pieces come out. So the only way we can fold it is across the center. And that is going to be at y equals -1. That's it. Now for this one, we have a couple options. We can fold it. Now it's a rectangle, so you know from making paper airplanes, rectangle, if you fold the diagonals, it's not going to match up perfectly if you do corner to corner, right? So we know we can't map the diagonals across, but we can fold it completely in half. Now, they will probably give you decimals, so let me show you the trick of how you get the half. All you do is count the boxes and divide by 2. So going up and down, there's 4 boxes. What's half of 4? 2. So I'm just going to go 2 boxes, and that's one of my lines. Y equals +1. Then I do the same thing going up and down, because we know with the rectangle, we can fold it long ways, and we can fold it up and down. So again, I count how many boxes across. I get 6. Does someone check my math? It's 5. It's 6. No, it's 6, dude. 6 divided by 2 is 3. Now look what happens. We get this lovely little cross in the middle, okay? We can't do diagonal symmetry, but we can do rotational symmetry. So look at right now, our long side is pointing up. If I rotate this 90 degrees, 360 divided by 4 is 90, is my long side still pointing up? No. But if I rotate it another 90 degrees, is my long side up? Yes. Not the exact long side, but still a long side. So not only do I have these lines of symmetry at y equals 1 and x equals -2, I also have rotational symmetry of 180 degrees centered around the point -2, +1. Okay, so we have multiple things in that case. Okay, I'm going to skip this one because I want us to move on. This is another way they're going to trick you. They'll give you the parallelogram. You can never fold a parallelogram, ever. The only time you can ever diagonal fold a parallelogram is if it's a rhombus. And this is clearly not a rhombus. A rhombus has all sides the same. So right away, we can cross off A and B, even though they drew those lines there, and be like, oh, I can just fold it. Nope, can't. It's not going to be A or B. So we're left with C or D. Again, in order for it to be rotational symmetry, you have to make sure the point is inside, like the steering wheel. The steering wheel has to be inside, so we're left at 2, 2. So the answer to number 10 is C. So far, so good? Anyone need me to clarify transformations? Because we're on to constructions. Okay, let's go quick through constructions. Constructing parallel lines, I'll put this on my e-class page. I'm not going to go over how to do constructions, but just as a reminder, parallel lines, we're pretty much looking for corresponding angles. Okay, congruent line segments, you're just kind of measuring, moving the compass again and measuring it again. I would be surprised if these two come up on your EOC. Congruent angles might come up. Basically, and again, you'll see this coming up, you're just going to mark, make a curve, put the compass here, make a little curve, and connect. So it's kind of like make one big curve, put a compass, make another curve, and then you do the same thing and you'll see where they match up. Angle bisector will absolutely be on your test. We're going to look at some examples of that. Okay, perpendicular bisector will absolutely be on your test. They might throw in doing a square, because all a square is after you draw your diameter, you do the perpendicular bisector of that diameter. So the perpendicular bisector would end up putting it about here, and then you connect the dots for the square. So they might give you that piece of it. And I have longer videos on constructions on YouTube. This one, yes, I do. This one, you're going to measure the radius from here to here. And then what we did is we put our compass on this one and we just kept going around the circle over and over again, and it ends up matching up perfectly. And then we connected the dots. For the equilateral triangle, a triangle is just half of 6. But let's look at questions. Look for where it says U1 con Q1. Everyone see it? Angle bisector. Okay? Wake up, you can do it. 20 minutes. Okay, here we're looking at a construction. Angle bisector. It's not going to be 2 or 3. So now we're left between 1 and 3. The answer is choice 3. Whenever you do angle bisector, first what you do is you draw an arc, and then these little pieces come from putting your compass on this point and matching them up. And that's how you draw your line. So the answer to QQ or U1 con Q1 is 2, or is 3 sugar shoots. For number 2, which could be the first step is always drawing an arc from the angle. So we look for angle, we put it here, and we put our compass there, and we draw the first arc. So it would be choice C. That's always your first step, is drawing an arc. Because we want to draw an arc from here to here, because after we do that, we're going to put our compass on this point and draw an arc here, compass on this point, draw an arc here, and that's how we draw the line. I know I'm doing constructions fast because it's easy to watch the video later. I want to get to congruence. Next, we have this right here. We have a diameter. We draw the diameter. This was I was talking about how to do the inscribed square. You always will do the perpendicular bisector. So what we did for the perpendicular bisector is we put the compass on the point, we went a little bit farther than halfway, and we looped up and we looped down, sugar shoots. Then we put our compass on the other point, we looped up, we looped down, and then we connected the points. So in this case, the next step of this construction is to construct the perpendicular bisector, letter D. Number 4, a student is working on geometric constructions. This is shown. What is it? This is going to be an angle bisector. Pretty much you can guarantee angle bisectors and perpendicular bisectors. If you have no idea what it is, guess one of those two. If it's an angle bisector. If it's a line, it's a perpendicular bisector. I would guess probably 80% of the time that's what it's going to be. Copying an angle will look like this. And measuring an angle, you wouldn't even use a compass for. Based on the construction below, which must be true. I'm not going to spend too much time on this. ABC is the bigger angle, and we know each of these pieces are smaller. So just come up with numbers. I'm going to call this 10, and because it's a bisector, each of those pieces have to be 10, which means that ABC has to be 20. So let's see, does ABD, well, ABD is 10. Is that half of 10? Well, half of 10 is 5, so that's not it. All I did was come up with numbers to check. ABD right here is this one, that's 10. Does that equal CBD 10? Yes, so it's choice 2. So sometimes it's just easier to come up with numbers and go from there, right? That way you don't have to pay attention as much to all those different letters. Okay. Some of you need to exercise personal space and get your books out. Next. So this one, it says, what's a perpendicular bisector? Please just know this. Make your life easy. 1. I think we did this today in some of our questions. Okay. Which principle is this one? This is copying an angle, and they form corresponding angles. So it's choice 4. I'm going fast on purpose. I just want you to have the answers, but that's how we copy an angle, is we do it because of corresponding angles. Okay, this one says not always true. That's why I put it up. Make sure you pay attention if they say not, because sometimes the first time we see something, we're like, oh, that's it. And we miss the word not. So we've got A, B, and CD is perpendicular. Yep, that's the definition of a perpendicular bisector. AB equals CD, that's the one that's not always true. Okay, AE equals EB, that's true. CE equals ED, that's also true. So it's number 2 is the one that's incorrect. Okay, I'm sorry I did that fast, but I really wanted to spend time on similarity. So dilations, easiest way to spot a dilation is there's a multiplication. That's it. So here, the official formula is KX, KY. You'll see it on your paper kind of in this section right here is where I talk about dilations. It's always going to have a multiplication. Remember, dilations can get bigger or smaller. Sometimes kids think dilations only get bigger. That's not true. They can get smaller. To find the center of dilation, which you will probably get at least one question on this, all you do is connect the dots. So for example, here we have our big one, here we have our small one. A connects to A prime, keep drawing the line forever. D and D prime, keep drawing the line forever. B and B prime, C and C prime, wherever they intersect, that's your center of dilation. So on the EOC, you're going to be taking it on the computer. So you're going to have to hold up a piece of paper to the screen and look through it so that you can draw the lines to see where they meet. Sometimes they're really nice to, and it's pretty obvious what it's going to be if you only do like 2 of them, okay? But all you do is connect the lines. So let's look. Which transformation results in a figure that is similar to the original, but greater area? I think we've done this in our class. Well, both of these numbers are less than 1, so it's going to get smaller. Like if you have $100, you don't want 25% of $100, you'd be stuck with 25 bucks. You wouldn't want 50% of $100, you'd be stuck with 50 bucks. This is, you have exactly $100, which is what you started with. That's not greater, so it's got to be 2, because 2 times 100 is 200. Something seems just too obtuse to you, just take a break and think, well, how can I make this relate to real life to help me get it through? Circle B is dilated to form circle P. Remember, it will not always get bigger. Sometimes it can get smaller, okay? So either one of these can be true. So the radius of P is equal. That only happens if the dilation is 1. So it's not choice A. The length of any chord in P is greater. Well, that only is if you get a smaller dilation, which you don't. So that's no. Move over. Separate yourselves right now. Diameter is greater than the other one. That's wrong. This is the one you need to know. And notice how I put that in bold print somewhere. You need to make sure that you remember, oh, here's the center of dilation piece. You do have to remember that it's a relationship between the ratio of the diameter and the circumference. Colin, do you have a question? Yep, question? Next one. This one I think we did. The center of dilation, we've already talked about that. The scale factor. Remember, we do new over old for the scale factor. So just pick any side you want. I'm going to pick the top because it's easy. So we're going to count boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes across. Our new one is 6 boxes across. New over old, 12 over 6 means our scale factor was 1/2. Okay, just count. That's it. What's the relationship between the pre-image and the image? The pre-image is twice as big as the image. Okay. This would be a good one. I don't think I've told you guys, but part of your EOC you will not get to use calculators for. There's only, it's because you don't need the calculators, so something like this would probably come up, or a trig question might come up. This one we've talked about before. Even though to find scale factor, we do new over old, but when it comes to doing the proportions, it isn't always new over old. So the answer to this one is going to be choice B, because I have AB, which is the pre-image over the image, pre-image over image. So it keeps the same pattern. This one's pre over the image, but this one's the image over the pre. It doesn't match up. So you need to make sure when we do proportions that you keep it the same. It's new over old when you find the scale factor, but when you're looking for proportional sides, it's not always new over old. This one's a repeat. This one I know we've done before. Just a reminder, whenever we do similarity, we're not looking at the sides. So this scale factor does not mean a gosh darn thing other than to confuse you. All that matters is the similarity is the angles. That's all that we care about. So this is 50, so this is 50, because it says ABC, XYZ. This is 100, so this is 100. This is 30, so this is 30. And that's our answer, 30 degrees. Sides proportional, angles same. Ma'am. Correct, ma'am. All right, guys, did everyone sign in on the sign-in sheet? Make sure you did. Okay, this right here is very important information, sugar shoots. It's also right here on this paper in your book and on the yellow paper. Things to remember, vertical angles form bow ties. Alternate interior, so this would be vertical angles, are these angles right here. Alternate interior angles, opposite sides of the parallel lines. Corresponding angles, top, top. Okay? Triangle sum is the 180 degrees. Don't forget isosceles triangles. That might be in there. The base angles are the same. The opposite sides are the same. Okay? Also, don't forget that with the perpendicular bisector, this one I went over, and I'm sorry I did. Let me go over that real quick. Whenever you have sugar shoots, woo! Whenever you have a perpendicular bisector, any point on here is the same distance no matter where it falls. So this point will be the same distance on each side. So there will probably be a question like that on your EOC. So you just have to remember, if they tell you it's a perpendicular bisector, these pieces are going to be the same. Let's look at some proofs. Okay, we'll go over proofs a little bit more in my class as opposed to right now. But don't forget, givens always come first. We talked about it being a sandwich. So the givens will always be the top. What you're proving will always be the bottom. And you kind of get to decide how you want the order of the ingredients to go. Also, don't forget to label it. This right here is a side. This is an angle. This is a side. So that helps me determine what my proof is. So sometimes just labeling the sides will help you. Okay, I'm going to just skip these because we'll go over them more. Go to U2Q8. U2Q8 should be on the second page. Okay, U2Q8. Let's take a look at it. It tells us HGK and IHU. So what type of angles are these two angles? Anyone got it? Who knows what kind of angles these are? If these lines are parallel. Are they both inside? They're corresponding, right? Alternate interior means they're both inside the parallel lines, which they're not. Alternate exterior means they're both outside the parallel lines, which they're not. Corresponding forms bow ties, and these aren't corresponding. So, or I'm sorry, they're not vertical. So that means they're corresponding. This one, I don't know why I put here. Oh, let's look. This one, it has translation, rotation. I put this in the wrong spot, but let's just look. Because it says translation and rotation, both of those are isometries, which means that they're congruent. And anything that's congruent is guaranteed similar. Guaranteed. So that's going to be congruent and similar. Okay, I'm almost done. I got like 5 more questions I want to cover with you. Which can be used to prove triangles are congruent. Let's label it. Here we have an angle. Here we have an angle. Here we have a side. So we know we have 2 angles in one side, so we know it's not choice A or choice C. This is when we talked about Chick-fil-A sandwiches versus school sandwiches. Remember how when we get Chick-fil-A or Zaxby's, they give us bread, chicken bread. But when we get our school sandwiches, we get the biscuit and the piece of chicken outside, and you got to put the chicken inside by yourself when you get the breakfast. Here, this side is not in between the angles. Here's my side. Here's one angle, here's the other angle. So because of that, the chicken is on the outside, so it's angle, angle, side. In order for it to have been angle, side, angle, we would have had to have our 2 angles, and our side would have had to touch both angles. Because this side only touches one, that's why it's AAS. It's not ASA because the side is not touching both angles. Question? We're good? Okay. Couple more. Question 11. Looking at question 11, it tells us that DE and JI are congruent. So pretty much this is one time where maybe you want to just redraw it so it matches up perfectly. This is an F, JIH. And that way you don't have to invert things. It tells you angle D and angle J match up. So angle D, angle J, and then these match up. It wants to know what additional information do you need? Well, this is testing. Can you find the hidden reflexive property? The hidden reflexive property is that we know HF has to be equal to HF because it's the same exact line. So this is reflexive. So we need to know, what are these extra pieces right here? Well, this piece is DH, this piece is FJ. So if we had DH and FJ, we could prove the entire line and do side angle side. Okay, you guys are doing awesome. Holy moly, I got 3 papers left. Okay, number 12. I know this is kind of a little bit blurry. It wants to know which one is here. It's not CPCTC because CPCTC is the bottom one, so we're not going to do that. So let's see how we match up. It tells us AD and BD. Well, that's a side. It tells us CD and CD. That's a side. It mentions right angles. So sometimes when we see right angles, we instantly think hypotenuse leg, but it's not always hypotenuse leg. So it tells us that right angles are congruent. So now we have our angle. So we know it can't be ASS because you know why. And there's no SSA. So it's got to be 2 sides and an angle. It has to be SAS. And I was kidding you. This is really our last one. So our last one is Q13. Here we've proven triangles congruent. And now we need to know, this is where it's proven by SAS. Usually speaking, what's going to come after SAS is CPCTC, which it does here. Corresponding parts of congruent triangles are congruent, because you have to have congruent triangles first. You'll never have congruent triangles till after. Okay, so listen up. We have 3 minutes left. You guys were freaking fantastic. Make sure you sign in on the, I know I said freaking, make sure you sign in on the sign-in sheet. Clean up the space so I don't have to clean up after you. Our next one is Monday. All things circle. We'll start more on time because I'll be more prepared. I apologize. I wasn't doing YouTube. And then next Friday is the big one. Make sure you sign up if